Right. Settle down, Velu. Good afternoon, everybody. Right. So this is the second week. Last week he started A-level work. Yeah, last week he started A-level work. Anyway, I'll do a small recap of whatever we did last week. Okay. Or whatever we did last week, basic work, I'll do it back again. And from there, we'll continue after that. Okay. Right. Now we are learning about what? Physical quantities. Now, how many fundamental physical quantities are there? 7 fundamental physical quantities. Is it clear? 7 fundamental physical quantities. What are your 7 fundamental physical quantities? Mass, length, time, dynamic temperature, electric current, substance of matter, luminous intensity. Clear? Luminous intensity. So you have 7 fundamental quantities. These are your 7. Mass, length, time, thermodynamic temperature. Thermodynamic temperature. Thermodynamic temperature. Electric current. Electric current. Substance of matter. Substance of matter. And then we have what? Luminous intensity. Luminous intensity. Okay. Right. So how do you represent this in the unit of measurement? Units are there. No? So mass is measured what? In kilograms. Length is measured in meters. Time is measured in seconds. Thermodynamic temperature measured in Kelvin, capital K. Electric current is measured in amperes. Substance of matter in mole. You lose this in chemistry. And luminous intensity, what is it? Candela, CD. Okay, no? Right. So these are your units: mass, length, time, thermodynamic temperature, electric current, substance of matter, luminous intensity. So these we call them fundamental quantities. What do you call it? Fundamental quantities. Fundamental quantities. Now, apart from this, there are 2 supplementary quantities. What are the 2 supplementary quantities? Plane angle, solid angle. Plane angle and solid angle. So 2 supplementary quantities, right on the side. Supplementary quantities. Plane angle and solid angle. Okay. Tell me, Vilu. Plane angle, what is the unit of measurement? Radians. Plane angle, unit of measurement, radian. Solid angle, unit of measurement? Steradians, SR. Clear? Now look at this carefully. Now, all our life, we have been measuring using what? Degrees. So we have never measured using radian. Okay? So there should be a relationship between what? Degrees and radians. There should be a relationship between degrees and radians. So what is the relationship between degrees and radians? Pi radians equals how much? 180 degrees. So anybody who was not there last week, so these are what we did. 7 fundamental quantities, 2 supplementary quantities, and we found a relationship between radians and what? Degrees. Now using this, we should be able to convert degrees to radians as well as what? Radians to degrees. So we solved a few examples as well. I'll do a few examples here also. Have a look. Observe. So let's say we need to convert 30 degrees to radians. So we follow a very basic procedure. What's the basic procedure? 180 degrees equals pi radians. 180 degrees equals pi radians. 1 degree equals how much? Pi over 180 radians. Pi over 180 radians. So like 10 toffees, 100 rupee, 1 toffee, how much? 5 toffees, how much? They're asking 30 degrees. What is the radian? So pi over 180 multiplied by how much? 30. So you just have to divide this carefully. 30 times 1, 30 times 6. So 30 degrees is equal to pi over 6 radians. Pi over 6 radians. Clear? We'll solve one more few examples. Let's say just to for the new ones. Let's say 45 degrees. You need to convert this to radians. So basic rule is what? 180 degrees equals pi radian. 1 degree is equal to pi over 180 radian. 45 degrees is pi over 180 multiplied by 45. How many 45s are there in 180? 90 has 2 45s. 90 times 2 is 180. So 45 times 1, 45 times 4. So here you have 45 degrees equals pi over 4 radians. Pi over 4 radians. Let's say for 75 degrees, convert this to radians. So basic rule again. 180 degrees equals pi radian. 1 degree is equal to pi over 180 radian. Pi over 180 radian. Here 75 degrees is pi over 180 multiplied by what? 75. So if you take this or do the calculation, 15 times 5, 15 times 1, 30 times 2. You will get 5 pi divided by 12 radians. So 75 degrees is 5 pi divided by 12. Yeah, 5 pi divided by 12. So there you go. That's how you convert what? Degrees to radians. Also, you can convert what? Radians to degrees. So what's the equation we are using? We are still using this equation. Don't forget. Very simple conversion. 180 degrees is pi radian. 180 degrees is pi radian. That's the conversion rule. Now look at this. Let's say we need to convert what? Degrees to radians done. Now radians to degrees. Let's say we need to convert pi over 3 radians to degrees. We don't know to find it. How are you going to find it? I'll go back to basic rule. Pi radian equals what? 180 degrees. Now, whatever you do to the left-hand side, you must also do what? To the right-hand side. Okay. So here, if you divide by 3, this side also you must divide by how much? 3. Clear? So here, if you solve it, 180 over 3 is going to be how much? 60. Look at this now. Let's say pi over 2 radians. Convert to degrees. So you know your basic rule, no? Pi radian equals 180 degrees. If I divide this side by 2, then this side also I must divide by how much? 2. 180 over 2 is equal to how much? 90. Okay. So not difficult, pretty simple connection. Let's say you need to find 5 pi divided by 12 radians. 5 pi divided by 12. Again basic. Go back to your original equation. What's the original equation? Pi radian equals 180 degrees. If you multiply this side by 5 over 12, then the other side also you multiply it by how much? 5 over 12. So now your division should be good. 12 times 1, 12 times 18 means 1. 6 left. 60 means 12 times 5. 15 times 5 is going to be how much? 75. 15 times 5 is going to be 75. So 5 pi divided by 12 radians, that is equal to 75 degrees. Clear? That is equal to 75 degrees. So you can see how we convert degrees to radians and what radians to degrees. Clear? Right. Then what we learned is we learned derived quantities. Now, for the ones who are not there last week also, listen very carefully from here, listen. What do you mean by derived quantities? A derived quantity is a quantity where we use fundamental quantities to make a new physical quantity. So we are using what? Fundamental quantities. What is fundamental quantity? Mass, length, time, thermodynamic temperature, electric current, substance of matter, luminous intensity. We are using those to make a new physical quantity. That new physical quantity is called what? Derived quantity. Is it clear? So I'm using what? I'm using fundamental. How many fundamental do I have? 7. I'm using those 7 to make a new physical quantity. Those new physical quantities are known as what? Derived quantities. Okay, derived quantities. Can we look? I think I did about 15, if my memory serves me correct. But there is some more, so we learn it. And then we go to the dimensions part. Can we look? Look. How many fundamental quantities do you have? 7. Using those 7, you're going to make new physical quantities. Those new physical quantities are called what? Derived quantities. Right, now can we look? We started off with something simple, I think. If the order goes here and there, just tell me. Right. We started with area. What is area? Length multiplied by breadth. Anyway, 2 lengths you're multiplying. 2 lengths you're multiplying. Length multiplied by another length. You all tell me. Length is a fundamental quantity. Right? No? Mass, length, time. MLT, remember? Mass, length, time. Mass is fundamental, length is fundamental, time is fundamental. Just remember those 3 for now. So length is fundamental. Fundamental. Using fundamental, I have made what? A derived quantity. So area is a derived quantity. I'm using fundamental quantities to make a new physical quantity. That is called what? A derived quantity. So area is what? A derived quantity. Right. Second one. Volume. Now what is volume? Length into breadth into height. How many lengths you are using? 3 lengths. So length multiplied by length multiplied by length. 3 lengths you multiply, you will get what? Volume. Volume is what? Fundamental or derived? Derived quantity. Why? I'm using fundamental quantities to make a new physical quantity. That new physical quantity is what? A derived quantity. Right. Third one. Linear density. This was a bit new for you all last week. You all know density, but not this one. So what is linear density equation? If you can remember, tell me. Mass divided by length. Good. Mass divided by length. Mass fundamental. MLT. Mass, length, time. Mass fundamental. Length fundamental. Using fundamentals, I make what? A derived quantity. Clear? I make a derived quantity. Fourth one. Surface density. If you were not there last week, at least this bit with me, slowly write it down. Huh? Important. Surface density. Surface density. Tell me somebody, what's the equation for surface density? Mass over area. Mass divided by area. Mass divided by area. Mass is fundamental. Area I can find using fundamental. Therefore, this whole thing what is a derived quantity. Clear? Whole thing is a derived quantity. Fifth one. At least what you know. Volume density. Volume density. So what is volume density? Mass divided by volume. Mass divided by volume. Mass fundamental. Volume I can find using fundamental. Therefore, this whole thing is what? A derived quantity. Clear? Whole thing is a derived quantity. Right. Have a look. If my memory serves me correct, speed, I think. Correct? Right. What is speed? Distance divided by time. Distance divided by time. Now, distance is what? A length. Distance, displacement, all of that is what? A length. Clear? So, distance is a length. Length is fundamental. Time is anyway what? Fundamental. Using fundamental, I have made what? A derived quantity. Using fundamental, we have made what? A derived quantity. So, speed is a derived quantity. Seventh one. Velocity. What is velocity? Displacement divided by time. Displacement divided by time. Displacement, length. Length is fundamental. Time, fundamental. Using fundamental, I have made what? A derived quantity. Clear? I have made a derived quantity. Eighth one. Acceleration. Correct, no? I'm just doing it in order. Acceleration. Acceleration is change in velocity. Change in velocity divided by time. Change in velocity is also velocity. Final velocity minus initial velocity is also what? Velocity, no change. So velocity I can find using fundamental. Time is fundamental. This is what? Derived. Ninth one. Force. Tell me the equation for force. Mass into acceleration. Famous one. Mass into acceleration. Mass is fundamental. Right? No, mass, length, time. Mass is fundamental. Acceleration I can find using fundamental. Therefore, force is what? A derived quantity. Force, derived quantity. 10th one is work. Pressure. I gave another word for pressure. What is it? Stress. This is another word that we use. This is mechanical stress, huh? Not the physical stress or whatever that you get. So pressure is force divided by area. Pressure is force divided by area. Force I can find using fundamental. Area also I can find using fundamental. Pressure or stress will be what? A derived quantity. Derived quantity. Next one. Work done. Work done is force multiplied by displacement. Force multiplied by displacement. Right. Force I can find using fundamental. Displacement is a length anyway. So fundamental, this is what? Derived. Fundamental, we have a derived quantity. Okay. Right. 12th one. Kinetic energy. Kinetic energy. Kinetic energy, half mass into what? Acceleration? Velocity squared. Velocity squared. Mass is fundamental. Velocity I can find using fundamental. So it's going to be what? A derived quantity. Clear? 13, gravitational potential energy. Gravitational, short form I write GPE. Yeah? Too long. Gravitational potential energy, mass, acceleration due to gravity, multiplied by height. Mass is fundamental. Acceleration I can find earlier using what? Fundamental. Height is a length, so fundamental. Using fundamental quantities, I have made what? A derived quantity. Clear? I have made a derived quantity. 14th, moment of a force. Moment of a force. Moment of a force. Equation is force multiplied by perpendicular distance to pivot point or rotational point. Perpendicular distance to pivot point. Yeah. Look at this carefully. Observe this carefully now. I gave another word for this. Moment of a force is also known as what? Torque. The spellings given there, T-O-R-Q-U-E. T-O-R-Q-U-E. Force I can find using fundamental. Perpendicular distance. Distance anyway is what? Length. No, length is fundamental. Using, I can get a derived quantity. Yeah, using this, I can get a derived quantity. 15th, strain. Strain. Now, if you have a rubber band, there is a natural length. If you pull it, it will extend, no? Strain is what? Change in length divided by initial length. Change in length divided by initial length. There you go. So far only we did last week. Yeah, we did last week. Also, we put the units of measurement. Length is measured in meter. Meter multiplied by meter, what? Meter squared. Meter multiplied by meter, meter squared. Okay. Volume, meter, what? Meter cube. Linear density, mass is kilogram divided by meter, take on top m-1. Surface density, kilogram divided by meter squared, take on top m-2. Volume density, kilogram divided by meter cube, take on top kg m-3. Speed, distance in meter divided by second time, take on top s-1. Velocity, displacement in meters divided by second, take s on top ms-1. Acceleration, velocity here is ms-1, time is s. If I take s on top, s-1, s-1, s-2, s-2. So here if you represent it, It's going to be S minus 2. What about force? Now, don't go and put Newton and all. Those we'll learn later, those units. We are writing in fundamental units. Mass is measured in kilogram. Acceleration measured ms minus 2. Kg ms minus 2. Kg ms minus 2. Pressure is force over area. Force is now kg ms minus 2 divided by meter squared. Look at this carefully. 1 meter you can cancel. 1 meter if you cancel, bottom you have to the power 1, take on top to the power minus 1. So here you will get kg m minus 1 s minus 2. What about work done? Force kg ms minus 2 into displacement meter. Meter into meter, meter squared. So here you will get what? Kg m squared s minus 2. Kg m squared s minus 2. There you go. This one here. Now here I gave you all a small special note as well. Now the question is, what is the unit of half? If they give you half, what is the unit? Now kilogram you have. Time you have. Velocity you have. What on earth is the unit of half? Half is unitless, no unit. So I taught you all, value constants are what? Unitless. So half, 3/4, quarter, pi, pi over 3, pi over 4, they have what? No units. Tell me now, unitless means what do you put? 0 or 1? 1. So here unitless means 1. I don't go and say half is equal to 1. No, no. Unitless means 1. Mass is measured in kilogram. Velocity is measured meters per second squared. Now simplify this carefully. Kg m squared s minus 2. Kg m squared s minus 2. Gravitational potential energy. So gravitational potential energy, mass is measured in kilogram. Acceleration ms minus 2, height is m. M and m squared. So m squared you can put here at once. Kg m squared s minus 2. Moment of a force. Force is kg ms minus 2 into distance m. Now what? Meter multiplied by meter, meter squared. So there you go, the units. Change in length. Change in length is measured in meter. Initial length is measured in meter. Meter, meter cancel off. Unit plus 1. So you call it what? Unitless. So this is what? A unitless quantity. Understood? Unitless quantity. So there is no unit. We'll show it as 1. So unitless. If you want put meter, meter, then that's equal to 1. Unitless. So how many special notes I gave you all? 1 special note. Value constants are what? Unitless. Unitless means equal to how much? 1. Okay. Now we continue from here. Have a look. 16th point. Observe, huh? Don't write. Look. There is a new physical quantity called linear momentum. New physical quantity called linear momentum. Linear momentum is defined as mass multiplied by what? Velocity. That means every mass which has a velocity will have what? A linear momentum. Perfect example for linear momentum is what? Let's say you're traveling by bus. Now, today you came by bus, no? To travel by bus. Bus is slowly slowing down. Just before you get down, just before the bus stops, some of the boys will what? Jump out of the bus and run with a little bit with the bus. You have seen this, no? When the bus is about to stop, before that you will get down. And you start what? Jogging a bit and then you turn back and go. My question to you is, Why on earth are you jumping out of the bus and running with the bus? Why can't you stop and at once turn? Bus is moving now. You jumped out now. You're not inside the bus now. Why are you running with the bus? Now, that's the point. When you're traveling in the bus, you have the speed of the bus. So bus is traveling at 10 kilometer per hour means you're also traveling at what? 10 kilometer per hour. And the fellows who sleep in the bus know this very well. Second, you're sleeping in the bus. At once the fellow applies the brakes. Where do you go? Why is your head going forward? Earlier, bus was going at 50 kilometers per hour. Your head was going also at what? 50 kilometers per hour. Your body is going also at what? 50 kilometers per hour. Bus apply brakes. Your body will now, body is connected. Your seat, no? Your body is connected to the seat. Seat is connected to the bus. So bus is slowing down. Seat is also slowing down. So this part of the body is slowing down. Head is what? Not connected anywhere. Head is moving. So your body is slowing down, but head is moving. That's how you go forward, knock on the front railing and come back. And then you will never open your eye because people are looking at you. So what, you keep on sleeping. When you go home, check and see the amount of pain you'll get, your forehead, your cheek. Best part is when they take the bend. You know. And then what, you can't open your face because people are looking at you and waiting. So what, you close your eyes and fall asleep. Knowing how painful it is, you know the process. This process you have undergone, you know. Sometimes mistakenly what will all your spit will drool down. You can't open your face. If they are looking at you, so what, you keep on sleeping like nothing ever happened. You have done this. This is you. Yeah. So that's the way. If you get up, then people will look at you. No, so you just keep closing. That's the way it goes. So the idea is that every object that has a velocity will also have what? A linear momentum. So the linear momentum is given by this equation, mass into what? Velocity. Mass into velocity. At once I'll put the unit toss and go, it's easier. Mass is measured in kilogram. Velocity is measured in meter per second. So kg ms minus 1. Kg ms minus 1. 17. Impulse. Impulse is force multiplied by time. Impulse is force into time. So if there's a large example, if there's a large force acting for a short time, when you play cricket, the ball comes, it strikes your bat and quickly the ball will go. So the ball is touching your bat for a long time or a short time. Short time, microseconds. Sometimes even smaller than that. So the moment it strikes, the ball goes. So what is happening there? A large force is applied on the ball. That's why if you keep on playing for a long time, the shape of the cricket ball will what? Change. Understood? The leather ball, the shape will change. That's because you keep on what? Knocking on the ground, coming to your bat, knocking on the ground, coming to your bat. You keep on playing it for a long time. What happens? The shape will change. Impulsive forces will act and change the shape. Same way, when the ball comes, it strikes your bat. The moment it strikes your blade, microseconds, object will start moving. So large force acting for a very short period of time creates what? Impulse. Clear? Creates impulse. So even when you fight, you all watch UFC and all. When you fight and all, check and see. You can create damage because of what? Impulsive force. That means you're applying a large force, very short time contact. I mean, people fight, they can touch like this and wait like that. No. Very quick. Then comes the next one. Is it clear? So the impulsive force generated, large force acting for what? A very short time. So here also, force unit is kg. Force unit is also kg ms minus 2 multiplied by s. Minus 2 plus 1 means kg ms minus 1. Kg ms minus 1. 18. Look at this carefully. Moment of inertia. New things, huh? Moment of inertia. Inertia is mass into distance squared. Mass into distance squared. Now, what is this moment of inertia? Moment of inertia is connected. Best example is a diver. When a diver jumps up out of a platform, check and see, the person has to somersault, twist, turn, enter water. When the person is doing a somersault, the body is what? Far away or close by? Close. When the body is close, rotation what becomes large. And when the person is about to enter water, what happens? He will stretch and then what? Enter water. So what happens is, when you spread your body, the rotation is going to be less. When you bring your body close, the rotation is going to be what? More. If you are living in a village, like I do, and if there's a canal or a river going, and if there's a bridge going on top, all of you all learn swimming there no first. Not in a pool. If you live in a village, city, of course, pool. Guaranteed you are going on top of that bridge, and then what? You jump down. Guaranteed. First time you jumped, this would have guaranteed happened to you. You would have fallen and your stomach will strike the water. Check and see the splash. And check and see the pain after that. Yeah. Check and see the pain after that. But with time you realize, no. If you enter, you should enter what? Arms in first, then head, and then you go. Or if you can't go like that, then you what? Jump out, stay vertical like this. And you go in. Is it clear? So you realize that by keeping your body spread, the rotation is what? Less. But if by any chance you bring your body close, then what? Rotation is more. At least once you've done a somersault. When you jump out of the bridge and you do a somersault, you just have to bring your body close by and then try to what? Recover it. Majority of the times you will just fall in your back to the water. But generally, if you try to recover, then you what? At least do one somersault. If you practice that, then you can get it. So anyways, the whole idea behind moment of inertia is that by changing your arm position, by changing your body position, you can change some rotational effects. And that is known as what? Moment of inertia. Is it clear? So when somebody says moment of inertia, you must remember what? The diver. The diver jumping out of the platform. Okay. You must remember the diver jumping out of the platform. So you put the units there. Mass is measured in kilogram. Distance is measured in meter squared. Distance measured meter squared. Right. 19. Angular momentum. Angular momentum. New things, huh? What is angular momentum? Linear momentum multiplied by the distance. Linear momentum multiplied by the distance. Don't write. Look, I'll give you time to write. Now, what on earth is this angular momentum? Okay, best example, let's say you go to a park. I don't know, in Kandy, I have not seen something like this, but anyways, let's say there's a park somewhere, you go to a park, and in a park, you have a merry-go-round. Have you seen a merry-go-round? I'm sure you have. So what is the first thing that you do normally, whatever your age, whether you're old or young or whatever, if you see an empty merry-go-round, what do you normally do? If you see an empty merry-go-round, nobody is there, what do you normally do? You will quickly run and jump on the merry-go-round. 1 round or 1.5 rounds, the merry-go-round will go and what? Stop. Clear? I don't know whether you will do that. I will do it. Is it clear? If you see an empty merry-go-round, that's a small kick, it's there. You just run and just what? Hop on it. You go one full circle, maybe a bit more, and then what? The merry-go-round will stop. Once the merry-go-round stops, you keep one leg out and what? Do this, and what? Go around. Generally, that's what you do, no? Now, what makes you go on the circle? Merry-go-round was at rest. You came running and you jumped on the merry-go-round and you went one full circle and you came. The quantity that makes you move like that is called what? Angular momentum. Clear? So the quantity that makes you move like that is known as what? Angular momentum. So whenever somebody says angular momentum, you should remember what? Merry-go-round. When somebody says moment of inertia, what should you remember? Diver. Somebody says angular momentum, what should you remember? Merry-go-round. You running and jumping on a merry-go-round, and the merry-go-round what? Going in a circle or two and stopping. Is it clear? Right. If you apply equations here, linear momentum, kg ms minus 1 multiplied by distance m. M into m will give you m squared. So kg m squared s minus 1. Kg m squared s minus 1. Right. Right. Look at this now. 20th. Surface tension. Surface tension. Force divided by length. What on earth is surface tension? Remember, without this, you can't even breathe. Without this, can't breathe. Uparwala. Clear? Your lungs work, oxygen, carbon dioxide, the diffusion takes place based on a very important quantity called what? Surface tension. When you bathe, the objective is what? What's the reason why you bathe? Clean our bodies. Very basic, no? Clean means what? You are dirty. Because you are dirty only, you should be what? Clean. And what do you use? You use soap. You use, I hope you use soap. Very clear. Or you must use what? Whatever cream or lotion or whatever that they do, like soap. You have no? Now, what is the objective? Check and see when you bathe. When you have wash, whatever, let's say you can play, you're stinking. When you do like this, you will get the gully, black color will come. Say it's like that. You just went and played. Full day you are playing, you're stinking. You can feel your own stink. I mean, my God, I stink well. Is it clear? There are moments like that, no? Let's say those moments. After you have a wash, when you're having a wash, check and see where the water drains out. There'll be soap forming and it'll be, dark gray. Have you seen? Dark grayishly it will go. What is that dark grayish substance that is going? Your dirt. Now, when you apply soap, why is dirt being, they say, use Lifebuoy, 99.99% the germs go. Like actually the germs say only 0.1% left. The advertisement is like that. Is it clear? So the whole idea is because of surface tension. So when you apply with Vicks of water, what happens is it will go and stick to the dirt particle. And once it sticks to the dirt particle can't go anywhere else. The dirt particle is stuck. Same in like in what you call washing powder. Now you put your clothes inside the washing machine, you put washing powder. No? The washing powder also works like this. The most difficult areas to wash is what? Boys, white color shirt, collar. Second seal, if you're washing by hand, you just keep on rubbing. Sometimes you just have to keep on rubbing, then only what? Finally it will go. That was 1 or 2 lines, somewhere it will be left. Clear? Now, but if you do it, let's say you apply, you put it in the washing machine or whatever, it will do the job. It will tumble and roll and something happens. And it's much more cleaner than when you're applying it. The reason is detergent also works like this. Now, if you take cloth, if you take your clothes, there are very small gaps like this now in the cloth. You can't see, the yarns of the thread are like that. Very close. There are very small gaps. So when you put soap or detergent or whatever, because of surface tension, this part is filled with those so detergent or soap powder. It'll go and stick to the dirt. And then when you wash it, you wash it at least, they say normally if you're washing by hand, at least 3 times you wash. Nalla pulinji edu. When you do that, what happens? Now the detergent is stuck with the dirt. No, the dirt will what come out. The objective is that. So it comes out because of what? Surface tension. So when you bathe today, the reason why you smell good after it, at least for a short period of time, it's because of what? Surface tension. Is it clear? Next is application. You're breathing because of surface tension. Now they say people who smoke, guaranteed lung problem. Lung is like a sponge, no? The sponginess will go. Why is your lung like a sponge? When you go home, go to your kitchen and take a sponge and see, you wet it only, nicely water will fall. That sponginess is there because what? It's generally full of fluid. Full of fluid means this effect is there. Inside it, somehow something is holding and waiting. That's surface tension. When you smoke, what happens is the tar in your cigarette or whatever goes and gets stuck to those sponginess. And now your lung cannot what be spongy. It can't what contract. It will be like a stone. And once it's like a stone, you can't what breathe. Every breathing is going to be difficult because this is not expanding and contracting. So you're trying to breathe, but you can't breathe. Why? This has to expand. It's not expanding. So whatever you're breathing, it's going to be very painful. It's like somebody stabbing you inside the lung. And then what? If you can't breathe properly, you can't give oxygen. Oxygen won't saturate. All the vital organs will slowly start shutting down, and then what? Death will come. Clear? So what helps you breathe? Surface tension. So I told you 3 things. Next, something fun. Now, early morning, mom has kept the tea. Somehow, an ant has fallen on the tea. The ant is running. You have seen this? No? So sometimes you take some fellows, of course, don't drink. Ant fell, I won't drink, and you throw it. Some fellows with the ant, they'll drink. Good. Some fellows will. Now, the ant may be having not any dirt, but your hand is dirty. They'll try to take the ant out, and therefore the tea is contaminated. Clear? So my advice is drink with the ant. Simple. No? Clear? Now, why on earth is the ant running on your tea? You have seen certain ponds also. Check and see. If you go on a pond, you will see some insects. They walk. They run on water. Why on earth are they running on water? That's because they have something called what? Surface tension on their legs. So when they stand on water, they won't sink. If you stand on water, check and see. Don't even try it. Because you do not have surface tension ability. Guaranteed you will what? Sink. Is it clear? For sure you will sink. Therefore, surface tension, even though the idea is a very simple one, force per length, the amount of applications is huge. Huge amount of application. Now when it's raining, why rain drops? At once, why like a waterfall can't it fall? Why rain drops are falling? Now you're seeing a waterfall, how water falls. So when it's raining, if it falls like that, what will happen? That means you're driving in a car, it starts raining like a waterfall, it hits your windscreen breaks, and what? You're floating in water and going. But when it's raining like that, drop by drop, no, it falls. Why is that? That's also because of surface tension. When the clouds are dark, that means what? It's about to what? It's full of ionized atoms, ionized particles. It's full of what? It's just about what? Break open and what? Condense and give you water. As the water, actually from the clouds, water is coming out just like when you take water in a sponge and you do this. Water will drip, no? Same way. But as it falls in the atmosphere, because of surface tension, the drops will break. And then smaller drops will fall on you. So from the clouds, actually big amount of water is coming. But as it's falling down, then what happens? As it's falling down, then what? It will break open. And then what? Small drops will what? Fall down. Best is when you're traveling by plane, check and see someday. Or you have seen this. One part raining, one part not raining. The rainy part you will see that region fully dark. It will be not be raindrops, it will be fully dark there, but somewhere down there'll be raindrops falling. Is it clear? Somewhere down there'll be raindrops falling. But that means as the water falls on Nivat, it will break into smaller parts. So that is based on what? Surface tension. So I've given you a lot of applications. Just remember what? Surface tension, very important. It's there in many places. Check and see when you now you drink, no, but let's say you buy Coca-Cola, you buy Sprite, you put a straw and you do this. You do that, no? And Coca-Cola, Sprite, whatever comes to your mouth. Why? Why is it coming up? Why can't it not come up? You put the straw, you do that, it'll come, no? Why? Why on earth is that? That's because of what? Your straw is there. Liquid is rising on the straw before it enters your mouth. So when you do this, you are creating a lower pressure inside your lung than the atmospheric pressure. So let's say this is your Mirinda bottle or whatever. You have put a straw. Here there is atmospheric pressure. This is where your mouth is. Inside your mouth, you do that, you create a low pressure inside your lung. Lower pressure than the atmosphere. Atmosphere will push this, liquid will what? Rise. Liquid rises also because of what? Surface tension. You will understand there is surface tension because the liquid will form a meniscus like this. Have you seen? When it falls a meniscus like that, guaranteed there is what? Surface tension. Understood? So I told you last week, physics is everywhere. Everything you do is based on what? Physics. There you go. If you apply here, force, kg ms minus 2 divided by m, you will get what? Kg s minus 2. Kg s minus 2. Right. Look at this now. 21. Planck's constant. Planck's constant, let's say normal symbol is h. Before I go here, I must teach you one more thing. You know this, but we'll learn that toss and go easier. 21 is frequency. O-level science. What is frequency? Equation. You should know this. It's there in your science book. 1 over t, very good. 1 divided by periodic time. Periodic time. Now 1 is a value. Value is unitless. Time is in second. S minus 1. Clear? S minus 1. 22. Planck's constant. Planck's constant. Don't write. Look and wait. I'll give you time to write this. Energy divided by frequency. Now, what on earth is Planck's constant? Energy is connected to some frequency. That's Planck's constant. This phenomenon happens to you every day in your life. Something that you should know is you have a particle nature. Now I can see your particle. You have a mass, you have a shape. Now you are at rest. In a little while you start running, then what? You have a velocity. So I can see your particle nature. You can see my particle nature. I have a mass, I have a shape, but I am now moving or not. That's called particle nature. But there is a wave nature as well. There is a wave nature as well. All of you all have a wave nature. We all have a wave nature. Clear? I'll tell you a place where this wave nature comes into play. Right. Answer this very carefully. Yeah? Let's say you're going somewhere for the very first time in your life. You have not gone there. This is the first time you're going. Huh? Example, let's say they're taking you on a trip to Polonnaruwa. You have never gone to Polonnaruwa. First time in your life you're going. So you're very excited. So you go by bus or train or whatever. And let's say you go by a vehicle and let's say you get down somewhere. When you get down somewhere, the place seems very familiar. Like you have been here earlier. Far away, you can see an old uncle traveling on a bicycle and coming. That also is very familiar. That also you remember. That uncle slowly comes, slowly comes, slowly comes, and you look at the uncle. Uncle's face is also very familiar. You keep looking. That moment, another small cat runs past the road. That cat is also what? Familiar. Tell me now. How many of you all have experienced that experience? Put your hands up. You have never been there, but the moment you go there, things become familiar. That moment your mom shouts, come. That is also what? Very familiar. The way she shouts also is very familiar. Then that moment your auntie tells something, that is also what? Familiar. You're wondering, when did this happen? This is the first time I have come here, no? Your mind is not working, you're thinking, but there is no way for you to think. You won't even know when because you have never been there. Right? This is the answer for that. Now, when you sleep, we sleep, no? We have a sleep cycle. When you sleep, you fall into something called the beta sleep. That means deep sleep around 1 o'clock at night. Deep sleep will last for about 2 hours, 1.5 hours to 2. Now, when you're fast asleep, exactly once you fall to the beta range, there is something called scientifically proven. Now, religiously, you call this the spirit or whatever. We'll not go to religion, we talk about science. There's something called the astral body. Astral body. How many people have heard about the astral body? Few people, right? Now what happens is, once you hit this beta range, the astral body will come out. The astral body will come out. Your astral body will come out. This astral body is connected to you just like a baby is connected to the mother in an umbilical cord, using umbilical cord. It's connected to you. It has infinite elastic ability. Yeah? It has what? Infinite elastic ability. And this astral body can travel infinite distances throughout space, away from space, different dimensions it can travel. It travels for about 1.5 hours to 2 hours. Now, this also you have experienced. Huh? When your beta sleep is about to finish, this astral body will come slowly and settle on your body. Exactly settle. When you settle, there's a small electric shock. Check and see. Some of you all are fast asleep. Around 2:45, at once you will get up. Sometimes you don't know even why. Why did I get up? Some people even don't know that they got up. They get up. And again, they'll fall asleep. Or Check and see if your mom is sleeping next to you, you get up, your mom will be like, again, you'll fall asleep. Let's say the boys get up. Maybe they'll get up and go to the washroom again and come and see who woke me up. And they're going to sleep. But generally, this normally happens. Even today morning, it happened to you. Huh? Sleeping, suddenly you get up. And then you're wondering, maybe some ghost has come there waking me up or whatever. A jinn is walking around my house. You start praying. Huh? No. Your astral body has gone on a big journey, come back and settle. The moment it settles, there's electric shock. An electric shock on you will feel. Now, this astral body, now I told you that place looks very familiar to you. That means now you might question. Now we'll stop the conversation. We'll talk about this later as we go along. We have 2 years to talk about this. Remember, the astral body travels to the future, to that moment. That means before you went on this trip, the astral body traveled there. It was waiting. It saw that uncle travel. It saw what? The cat cross the road. It saw your mama shout, "Come here." She shouted. It saw your auntie tell something. It saw your auntie and mama fight together. Clear? Everything it saw. And that's why when you go for real there, in your subconscious memory, this moment looks what? Very familiar. Check and see when some people talk to you, whatever word they say, next word you can predict. Because what? That moment looks very, very familiar. That's because you have been there. Remember, this astral body is very powerful. It can travel to the future as well as what? Past. Remember, developed countries, they use this as a soldier. Imagine if you can control the astral body, it can travel to places where no one can travel and get information, come back. If you can take that information back again into proper data, you can what? Do a lot of things. All you have to do is train the fellow to properly what? Sleep. I'm sure Sri Lankans can be what? Put into that category. Problem is, will they remember it after they come is a problem. We are good to sleep. You can sleep very well. Is it clear? Now, so remember, so your wave nature, that is your wave nature. If your mom got up before that and looked at you, mama can see the particle nature, they are sleeping. Can your mom see the wave nature? No, wave has gone. Wave has gone on a small journey. And it will come back. What do you mean you're dead? You're dead means this cord here, the connection cord is cut. So when you die someday, same thing happens. You will feel as if what? The tunnel vision comes, everything becomes what? Much more closer. Your former memories start playing backwards. The memories will play backwards. From the moment you are there, it will play backwards. That's because your hard disks are getting empty. Whatever you stored, your hard disk, let's say you're keeping in files, all the files start what? Getting released. So quickly, flashback will come. Your small days, your uncle, your auntie, how you played, your brothers, sisters. Someday it will happen to me before y'all. So I will go through this process much more quicker than y'all. Someday when y'all also reach that point, this thing will happen. Nah? You won't remember then, this is told like that. Because what? Everything will flashback. You go slowly back again, what? Towards that initial point where you were born. Then what? Cord cuts off. Clear? And then what? Your astral body is released. People call it the spirit. Different religions tell different things. It moves away. There you go. That's how it ends. There are noted places where the astral body was there watching. There are instances. There are some medical operations. Clear? When they were operating, let's say after accident, they're operating. The astral body is there on the corner of the operating theater looking at the body. I'm not joking. When the fellow came to life again, he was telling, I was there in the room. I saw my heart was not breathing. I was not breathing. Then the doctors are doing this. There were so many nurses working. There are a few nurses like this. Everything they'll tell, documented evidence is there. That's because your astral body was there looking at the whole process. came back again because what? This cord was not severed. But if you call it the silver cord, in literature they call it the silver cord. Before the silver cord is what? Severed. Severed means what? Cut. Is it clear? So different religions believe in different things. Who decides when to cut this? Some people say God, some people say karma, etc. But that one moment, what happens? Silver cord is cut, and this is what? Released. So that's how it works. So that is what your wave nature. So whether you like it or not, the wave nature is there. And we believe in this wave nature as well. So that's why they say when you're living, do good. So you'll end up in a better place. Why is that? People actually believe that there is this wave nature is there. You won't be physically there, no? Let's say when you die, when you go to heaven, how are you going? You're wearing tie, what you call full suit with tie, and then entering what heaven? Like, hello, I came back. No. How are you going to go? Your wave form only will go. Your energy form only will go. Is it clear? If there's a place like that. So that energy form only you believe. And to make sure your final energy form goes to a better place, only you are do good things, etc., etc. Is it clear? So that's the whole idea, okay? So Planck's constant talks about this wave nature. Is it clear? Planck's constant talks about this wave nature. You can do more research when you go home about this. So I think I have given you a good start. You can learn about these things. Yeah, scientific, important. So now, if you put the units, energy same as work, kg m squared s minus 2. Frequency s minus 1, you can say kg m squared s minus 1. Kg m squared s minus 1. Sorry. 23. Look carefully. Let's say relative density. Relative density. Relative density is density of a substance. Density of a substance divided by density of water. When they say density, it's volume density. Yeah? Density of water. Density of a substance. Density of a substance. You know the units kg m minus 3. Here also kg m minus 3. Kg m minus 3, kg m minus 3 cancel off. It's 1. 1 means what? Unitless. Unitless. Look at this, huh? Refractive index. You call this specific gravity also. So if you see the word specific gravity, don't panic. Specific gravity is also what? Relative density. Refractive index. Refractive index, O-level science. Sin I divided by sin R. Sin I is a value. Values are what? Unitless 1. Sin R is a value. What is it? Unitless. So unitless will give you what? Unitless, no unit. 1. 25. Look. Observe. Huh? Angular, listen carefully, angular velocity. Now you might say, sir, angular velocity means what? Now if you take a fan blade, should tap it, the fan blade will go like this angle. Tap it, it will go another angle. But if you tap it, it's going with the speed. Tap it, it's going with the speed. Tap it, it's going with the speed, a particular angle. Clear? We define this as angular velocity divided by what? Time. Sorry, angular displacement over time. Angular displacement divided by time. Angle, no? Angular displacement divided by time. Velocity is displacement over time. Angular velocity is angular displacement over time. Imagine a fan rotating. Now, what is this angular displacement? Angular displacement is plane angle. Angle. Clear? So how do you measure angle? Tell me. How do you measure angle? Radians. Very good. Radians. That. Time in second. Take on top. What do you get? Radians per second. Radians per second. Maybe we'll add a few more here. Let's say angular acceleration also, because this is something new for you all. Angular acceleration. Angular acceleration. Angular acceleration is change in angular velocity over time. Change in angular velocity. Change in angular velocity divided by time. What is the change in angular velocity? Change in angular velocity is also angular velocity. Radians per second divided by second. Take on top. If you take on top, what will you get? Radians per second squared. Radians per second squared. Clear? So we can keep going like that. But the main idea is what? If I use fundamental quantities, I can make what? New physical quantities. Those are called what? Derived quantities. If somebody tells you moment of inertia, what should you remember? If somebody says moment of inertia, what should you remember? Diver. If somebody says angular velocity, what should you remember? If somebody says angular velocity, what should you remember? Fan. Just now I told. Where has your astral body gone? Clear. If somebody says angular momentum, merry-go-round. If somebody says surface tension, so many examples are there. Just imagine you bathing, that's enough. Clear. Imagine you bathing and the dirt going from the what you call water exit. Clear. If somebody says Planck's constant, what will you remember? Astral body. Your wave nature. Clear, no? We stopped it. If somebody says linear momentum, if somebody says linear momentum, bus, you are inside the bus. If somebody says impulse, then what? Hitting a ball, cricket bat hitting a ball. Okay. Right, Dulu? 16 linear momentum. Sorry, right? Linear momentum. Right? Anybody still writing this? Quickly write, quickly write. Okay, finished. Finished. Right. Right. Right? Now look at all your, we wrote 26 terms, right? Look at all your 26 terms. So you can see there are some physical quantities which have the same base units. Look at speed and velocity. Speed and velocity, same base unit. What else? Work done, kinetic energy, gravitational potential energy, torque. Same basic units. Look at linear momentum impulse. Same basic unit. Clear? Turn and look, turn and look. Linear momentum impulse, same basic unit. What else? Angular momentum, Planck's constant. Same basic unit. Is it clear? Same basic unit. There are some physical quantities which have what? The same basic unit. And also there are some physical quantities with no unit, unitless. What are they? Relative density, specific gravity. What else? Refractive index, strain. They have what? No units. They are unitless. Okay. Write this special note. Write special note. There are some physical quantities. There are some physical quantities. There are some physical quantities which have equal base units. Which have equal base units. Which have equal base units. Put 1, 2, 3 and write. First one, speed and velocity. Speed and velocity. Second one, work done. Work done. Kinetic energy. Work done. Kinetic energy. Gravitational potential energy. Short form you can write GPE also. Gravitational potential energy, comma, moment of a force. Moment of a force, or we can call it torque. Moment of a force, or we can also call it torque. Moment of a force, or we call it torque. And next point, linear momentum impulse. Linear momentum impulse. Linear momentum impulse. Linear momentum impulse. What's the next one? Planck constant angular momentum. Planck constant angular momentum. Right. Next special note. Right. There are certain physical quantities. There are certain physical quantities. There are certain physical quantities which are unitless. There are certain physical quantities which are unitless. What are examples? Strain, refractive index, relative density. Strain, refractive index, relative density. Okay. There are some more things will be added as we go along. So keep maybe one line more to write those things, addition. Okay, no? Right. So you learn 7 fundamental quantities, 2 supplementary quantities. You know the convert how between degrees to radians and radians to degrees. And then you know, using fundamental quantities, we can make what? Derived quantities. Yeah, derived quantities, right? Now we move into dimensions. Dimensions. Now what on earth is dimensions? Dimensions is not 1D, 2D, 3D. That's Cartesian maths axis. No? X, Y, Z. What do you mean by basic dimensions? Look carefully. Yeah? Now you have done 26 examples. No? Our next target is for these 26 examples, you are going to write dimensions alone. There. You're going to do this alone. So carefully listen. Now let's say in Sri Lanka, we measure using SI unit system. Let's say I want to measure mass, it's in kilograms or grams. But if you go to America and you measure, there they measure in pounds and ounces. There they don't use kilograms. You have to measure in pounds and ounces. Sometimes they measure in stone. How many stones you are? That means they have a standard stone. Comparing to that standard stone, what is your weight? Yeah. Now, they are measuring in a different unit system. We are measuring in a different unit system, but we are measuring the same thing. Here also we are measuring mass. In America also we are measuring what? Mass. Here we measure length in meters. In America they measure in what? Feet. Units are different. But what are we measuring? The same thing. Length. So they realize different countries use different systems. India has MKS system. Then they have their own imperial system, all unit system. Chinese have their own one, Japanese have their own one. So different countries, they use different measuring units. You can't stop that. But what they are measuring scientifically is the same thing. They are measuring what? Mass. So the universal scientific method of representing a physical quantity is called what? Dimensions. That means, let's say you go to Japan someday. I mean, Japan, they won't talk in, they might know English, but they won't talk English. They never write in English. Everything is in Japanese. You have to study yours in Japanese. They won't teach you in English. There is no university that teaches in English there. Everything is what? In Japanese. Even there, they recognize what a dimension is. They might put in Japanese letters, but there is a standard method to represent. This is the standard method. Carefully look. If there is a physical quantity and the universal method of representing it is called what? Dimensions. Dimensions. How do you represent a dimension? Look at this carefully. Let's say dimensions of mass. Dimensions of mass. We represent it like this. Mass square bracket. Square bracket. We can't put any bracket we want. We can't be putting curly like this. No, you can't do those. What's the method? Square bracket. So even in Japan, if they write in Japanese and they put square bracket, you know it's what? A dimension. So the universal method of representing a dimension is called what? Representing a physical quantity is called what? Dimensions. And the symbol that we use is what? Square brackets. So dimensions of mass is represented as capital M. Dimensions of length. Dimensions of length. Dimensions of length means length square brackets. What is it? Capital L. Dimensions of time. Dimensions of time. That is time square brackets. What is it? Capital T. So you're representing, if they ask you what is this dimension, they are asking the scientific representation. That's it. Is it clear? So mass dimension means capital M. Length dimension means capital L. Time dimension means capital T. Mass, length, time. Others also there. As we go along, we learn those. For now, mass, length, time important. So dimensions of mass is capital M. Dimensions of length is capital L. Dimensions of time is what? Capital T. So what is the dimension? Universal method of representing what? A physical quantity. Clear? That's right. Subtopic dimensions. Subtopic dimensions. That's right. The universal method in representing a physical quantity, the universal method in representing a physical quantity is known as dimensions. Is known as dimension. We always represent dimensions. We always represent dimension we always represent a dimension using square brackets. Using square brackets. Quickly represent this. Dimensions of mass, capital M. Dimensions of length, capital L. Dimensions of time, capital T. Okay, look at the next example. Right, look. Now you're going to represent, all of you are going to represent the 26 physical quantities, derived quantities you learned in dimensions. Now what's the first one? Go back to your derived quantities. Area, no? We're going to start there. Now, area square bracket means dimensions of area. Now, what's the equation for area? Length multiplied by length. So you can write this length square bracket multiply by length. Length dimension is capital L. Length dimension is capital L. L times L is what? L squared. So dimensions of area is going to be what? L squared. Clear? So you should know the equations. Turn back and look nicely, right, and write it. Huh? Next one, look. Volume. Volume square bracket means dimension of volume. No need to write all this all the time. This I just showed it to you all. Now, dimension of volume. What is volume? Length multiplied by length multiplied by another length. length square bracket. What's the dimension of length? L into L into L. What is it? L cube. So dimension of volume is L cube. I'll do one more, then you must do it. Huh? Third one. Linear density. Linear density square bracket means dimensions of linear density. That is mass divided by length. So mass square bracket, length square bracket. Mass is M, length is L. ML minus 1. So dimensions of linear density is what? ML minus 1. Okay. Write a small sentence. Write the dimensions of the following derived quantities. Write the dimensions of the following derived quantities. Now remember, you have 26. Huh? All 26 you must write what? In dimension form. So I have given you the first three. Area, volume, linear density. Right, Will? Area, volume, linear density. Others keep on working. Turn back, look at the equations, keep writing. Next one is, I think, surface density, volume density, that will continue. So I told all the ones who were not there also to write it now if you're not here. Now, Cafe, look at your equations one by one, keep going. Keep working. You have 26, so 23 more. right? So right. So up to linear density we wrote, no? Put the dimensions here. Look. Surface density square bracket. That's mass over area. Mass is m, area is L squared. Your answer should be ml minus 2. I hope you got this. Volume density is mass divided by volume. Mass is going to be m. Volume is L cube, take on top. ml minus 3. Speed, distance divided by time. Distance is going to be L divided by T. LT minus 1. LT minus 1. Have you got those correct? Okay. Right. Next is velocity dimension. Displacement divided by time. Displacement is L, time is T, LT minus 1. Acceleration. Acceleration. Change in velocity over time. Change in velocity is also velocity, LT minus 1. Divide by time, this will give you LT minus 2. Right. Force dimension. Very famous one, you should remember this. Huh? Mass into acceleration. Mass is m, acceleration LT minus 2, MLT minus 2. Clear? MLT minus 2. Pressure dimension, force divided by area. Force is going to be MLT minus 2 divided by L squared. ML minus 1 T minus 2. ML minus 1 T minus 2. ML minus 1 T minus 2. See whether you got these. Huh? Work done. Force into displacement. Force is MLT minus 2 into L. What is it? ML squared T minus 2. ML squared T minus 2. ML squared T minus 2. Have you all got this? Anybody writing this? Anybody writing this? No one. Okay. Next one. Kinetic energy. Now units will remove. Kinetic energy square brackets. Half mass. Don't worry, you can put it here itself. Velocity squared. Shh. Now values are dimensionless, no values, no dimensions. Dimensionless means how much? 1. Clear? Put a small special note there. Put a special note there. Value constants are dimensionless. Value constants are dimensionless. Value constants are dimensionless. Value constants are dimensionless. Example put. Half dimension is 1. Pi dimension 1. 3/4 dimension is what? 1. Okay. So here if you substitute 1, mass is m, velocity is LT minus 1 squared. You will get ml squared t minus 2. Did you get this? Gravitational potential energy, mass, acceleration due to gravity, height. Mass is going to be m, acceleration due to gravity LT minus 2 into height is L. L and L becomes L squared. L squared, there you go. ml squared t minus 2. Moment of a force. Force into perpendicular distance to pivot point. Force is going to be mlt minus 2. mlt minus 2 multiplied by distance, so becomes L squared. So this becomes L squared. Strain. Change in length is a length. Change in length is a length. Initial length is a length. L divided by L is what? 1. 1 means what? Dimensionless. 1 means dimensionless. See if you have got this. Anybody writing this? Anybody writing this? No one? Okay. So strain means what? Dimensionless. Huh? Yeah. Strain is dimensionless. Right. Linear momentum. Before we'll erase the unit. Linear momentum mass into velocity. Mass is m, velocity LT minus 1. Impulse. Force into time. Force is mlt minus 2 into t. Minus 2 plus 1 means mlt minus 1. mlt minus 1. Moment of inertia. Moment of inertia is mass into distance squared. Mass into distance squared. ml squared. Angular momentum. Linear momentum into distance. Linear momentum mlt minus 1 into L. That's ml squared t minus 1. ml squared t minus 1. Surface tension is force divided by length. Force is going to be what? mlt minus 2 divided by L. mt minus 2. There you go. mt minus 2. Anybody writing this? Writing quickly, right? Did you all get these answers? Okay. So moment of inertia, ml squared, angular momentum, ML square T minus 1, surface tension MT minus 2. Surface tension MT minus 2. That's capital. You mean inside the bracket what you're writing? Those are no need. Yeah, there is no problem. Clear. Important thing is what you write outside. Okay. In other words, here or L is simple. There is nothing there. Okay. Right. Frequency 1 divided by periodic time. We'll erase the units. Right. 1 is a value dimensionless time here. T minus 1. Planck's constant. Energy over frequency. Energy is ml squared T minus 2. Frequency is T minus 1. ml squared T minus 1. Relative density. Density of substance divided by density of water. Dimensionless 1. If you want, you can write like this. So ml minus 3 divided by ml minus 3 is 1. Refractive index sin I divided by sin R. Value means 1. Value means 1. Angular velocity. Angular displacement divided by time. Listen very carefully. Special note. Supplementary quantities are dimensionless. Supplementary quantities means what? Plane angle. Plane angle. If somebody puts square bracket, it's 1. Solid angle. If somebody puts square bracket, remember it's 1. Supplementary quantities are dimensionless. Right on the side, huh? Special note. Supplementary quantities are dimensionless. Supplementary quantities are dimensionless. So you can write there. Plane angle means 1. Solid angle means 1. Plane angle means 1. Solid angle is also 1. Okay. Angular velocity. Angular displacement is a plane angle, dimensionless. Time is t. Answer is t minus 1. Answer is t minus 1. Angular acceleration is change in angular velocity divided by time. Change in angular velocity is angular velocity t minus 1 divided by time t minus 2. T minus 1, t minus 2. Okay. Right now, cafe look. See the quantities which have the same dimensions. But speed and velocity. What else? Work done, kinetic energy, gravitational potential energy, torque. What else? Linear momentum, impulse. What else? Angular velocity and Planck constant. No. Angular momentum and Planck's constant. What else? What else? What else? Don't look at my face. Look at the book. No. Which has dimensions. Which one? Angular velocity and frequency. Okay. Let's write, Bill. Let's write. The following quantities have the same dimensions. Special note. The following quantities have the same dimensions. Following quantities have the same dimensions. Right. Point form, right? First one, speed, velocity. Speed, velocity. Speed, velocity. Next one, right? Work done, comma, kinetic energy, comma, gravitational potential energy, comma, torque. Next one, linear momentum, impulse. Linear momentum, impulse. Linear momentum, impulse. What else? Angular momentum, Planck's constant. Angular momentum, Planck's constant. Angular momentum, Planck's constant. Next one, frequency, angular velocity. Frequency, angular velocity. Okay. Special note. There are some quantities with units, but no dimensions. Example. There are some quantities with units, no dimensions. No. There are some quantities with units, have unit, no dimensions. Huh? Plane angle, solid angle. Plane angle, radians, solid angles, the radians, no dimensions. Have unit, no dimensions. Clear? Right there. There are some quantities. There are some quantities. There are some quantities with a unit. There are some quantities with a unit, but they are dimensionless. But they are dimensionless. But they are dimensionless. Right there. Plane angle, solid angle. Plane angle, solid angle. Okay. Right. So for today, whatever we are doing, done. Now remember, next week onwards, we start the application part. Applications of dimensions. Clear? Right. Close your books, hello. Right. While closing, listen carefully. Okay. Now, because of your request, because most of you are requested, we've got the two teachers that you are requested. Some of you are requesting a good maths teacher, and then a good somebody who can teach what you call chemistry, so that you will understand. Clear? So there are two teachers here. First one, chemistry, I think all of you have got the leaflet, minus sir. So he'll be starting the class next week. And then from Kurunagala, we got the leading teacher there, Rajika Vimaratna. He'll be coming next week onwards. So the dates will be given to you all. So further information, you can ask from the office. Is it clear? So you can discuss and you can sort your doubts as you study. Okay, right then. Okay then, next week, don't forget, we'll be starting applications. Important. Get home safe.